Hey, this is Alex. Welcome back to the project. Today is episode 2 of our mini-series on the electronics. We're going to be covering the schematic, taking our block diagram from last episode and converting it into a schematic that we can then use to make a PCB. Let's get into it. There are countless ways to make a schematic in a circuit board, but one that's my favorite to use is called EasyEDA. And it's an online schematic and PCB editor. And the reason that I like it is because it is an integrated environment with two other services. One is called JLC PCB, which is a PCB manufacturer, and then the other is LCSC, which is an electronics supplier. And the really cool thing about all these is that you can design a schematic, convert it to a circuit board, populate it with components that are found on the LCSC store, and then you can have the PCB manufactured and assembled with the components all in one place. So we're going to open up a new project here, and I'm going to walk you through how to make a schematic. So I've got a blank schematic page here. And I've already selected the components ahead of time that correspond with the block diagram that we just drew. So I'm going to run through how to put those components onto the schematic, and then I'll do a demonstration of one component or a couple components, and then I'll just fast forward through so you can get a sense of what I'm doing, but that it won't take an hour or so. You can do place, device, reuse block, or the Shift F, and then you can look up components. And it's most helpful if you're going to use the LCSC, which this one kind of defaults to have that LCSC part number handy ahead of time. And it's usually easier to look up the components on the LCSC website rather than here. So for example, this is the part number for this boost regulator. So we're going to put that up there. Okay. And then we need a couple more components for the boost regulator. This is the inductor that will go here. And then we'll need a couple of common components. So there's this tab over here that has common components for things like resistors, capacitors, diodes, and then common other packages, pin headers and such. And so we will need some surface mount capacitors, and there's different sizes. We're going to use some 0603, and we'll place a couple of them here, and then we can modify the values later. So we want one to be 100 nanofarads is fine, and we want one to be 10 microfarads. And then this one, 10 microfarads. And where I'm getting this is if you're ever working with integrated circuits, working with integrated circuits is more like putting together Lego blocks than anything else. And if you know what kind of integrated circuit that you need, for instance, a power supply that takes a low voltage and boosts it up to a higher voltage, you can find devices on LCSC's website or other component houses like Mouser, DigiKey, and then they'll usually have an application diagram and maybe some guidance on how to choose different sizes of components, and maybe sometimes even a layout, a PCB layout. So here's our typical application circuit for this little BL8536 boost converter. We have the VN node, and that goes to a 10 microfarad capacitor to ground, a 2.2 microhenry inductor to the SAW pin. The out pin has a 10 microfarad capacitor from out to ground. So that's basically what I've done. Okay, and then to connect them all up, we'll just use the wire tool. We'll just click our way to the connections. Okay, and then we'll get a ground node. Ground. This is a ground net that will connect anything that we put this to will be connected to the same net. So we'll use this a little bit later on to connect all of our ground things to. Okay. Alright, and then just like that, we've got one little circuit element connected. This is our power supply. So we'll have a battery input. We can put that here. We'll call this VBAT. And this is just a little net marker. So, and connect that there. And then the other side, we can choose a different looking net here, as sometimes common. And there. Okay, so that's going to be our VCC, or we can call it VC 3.3, whichever. Doesn't matter, the name doesn't matter. What matters is what it's connected to, so that anything that has a VCC wired to it will have the same net, and then once we move to the PCB, then those nets, anything that's connected together, will show up and help us connect together. So I'm going to start placing components on the board, and we'll fast forward through this section. And then once I reach the end, I will explain all of the different circuit elements and what they correspond to on our block diagram. Okay, so we finished our schematic. Let's go ahead and walk through it. So up on the top left here, we have the boost converter that we saw, and it's going to take a battery voltage, a 1.5 volt battery, and boost it up to 3.3 volts on this side. So input here, VBAT, output VCC. Over here we have this, our reverse battery protection MOSFET, and how it works is the gate is pulled up to this rail here, so when the gate to source voltage is high enough, so it's a positive voltage between here and this rail, then this MOSFET will turn on and let current flow in both directions. So this will be like a switch. And then if the battery was reversed, then the gate to source voltage would be negative, so the MOSFET would be off. So that would not let current go through from this header to ground, which if we didn't have this MOSFET and we flipped the battery, we would have current going from ground through the circuits, through battery, and it would likely damage our microcontroller and other circuits. So that's that. Over here we've got our microcontroller. This is our BM15M unit, and we'll take a look at this a little bit later, but this is our kind of, it's more than just a microcontroller. It's a whole little FCC certified module. But essentially we'll treat it like a microcontroller here, and we've got our different connections. We have our N64 pin, the VBAT. This will be an input for the battery measurement, so it's an analog input. Then, and our N64 power control to turn on and off power to the controller itself to save battery. These resistors are going to be for our ECU ID, so that we can decide, we can populate one or the other to tell the software that the device is a controller module or a console module. Down here we've got a crystal oscillator, a 32 kilohertz crystal oscillator, which will be used for our low power modes. It will be able to keep track of time while the circuit's off, and the low frequency consumes a lot less current than a high frequency crystal oscillator. So that's what that's for. Down here over on the bottom, we've got our push button switch for different modes, different syncing modes, and turning the module on and off. We've got the LED controls. We've got a four color discrete LED package, so one control for each color. We've got the reset line that's pulled up to high 3.3 volts, and we won't actually control the reset here, so this will just be pulled up to VCC. So as long as there's power, then the microcontroller is on. And then on the top, we've got these two nodes for programming, so the clock and the DIO lines, and those will be used for flashing the software. Okay, down here we have our LED and current limiting resistors for each discrete LED in this package, and then we'll have MOSFETs that will control the LEDs. So each of these signals will go to a gate, and then when that signal goes high, then the MOSFET will turn on, connect power to these different nodes, and the LEDs will turn on. And over here we've got our another MOSFET, a P-channel MOSFET, that will, when this node is low, it will turn on this MOSFET to connect power to the N64 controller, and then when we turn this node off, or a logic high, then the power to the controller will turn off. So we'll be able to save battery since the controller consumes quite a bit of power, and we don't need it to be on all the time. These are pins for the N64 controller: power, data, and ground. And then last but not least is this programming interface. We just have test points that we can connect to right now, these 4 different test points. To be able to program the part, we need power, clock, data, and ground. So now that we've got our schematic finalized, we're going to take the next episode to place and route components, order the circuit boards, and assemble them. Stay tuned, and see you in the next one.